So Ali
Right.
Chamseddine will tell us about discrete gravity. So you have half an hour. Please go ahead.
All right. Okay, so I'm really honored to be speaking at Hermannfest, and I would have loved to come in person, but visa regulations prevented me from being in Germany at this time. So I will start by saying, actually, the first time I saw Hermann was at CERN, 1980. So he was a fellow at CERN, and I was some research associate at the time. And then he gave a seminar talking about none other than the Nicolai map. And I was really very impressed by, that at this young age he had a map named after him. So that was my first encounter with Hermann. And since then, actually, we became friends. So today, the title of my talk, or Discrete Gravity, it's some work I've done last year with Slava Mukhanov. And this work actually is an attempt to make, to define differential geometric analogues of curvature and Riemann tensor and so on that go smoothly in the limit to the usual expressions of differential geometry. And so we, let me see. I have to go to next page, actually, 1 second. I have to go this. Yeah, because I cannot see its full screen. Okay, I can do it with the finger. Okay, so my main motivation is that at Planck scale, points are indistinguishable. And one can think in terms of, quanta of geometry, that there must exist some quanta, very small, either in the form of spheres or cells. And the aim of the work actually is to associate geometric invariance with the discrete structure, with discrete spaces, such that those reduce in the continuous limit where the characteristic length of the cells really go to zero, and so that in the limit we really get the familiar expressions, we obtain differential geometry. So this is the motivation. And so the model we think of actually is that we have to replace, say, blocks with cells and assume that every cell is gel-like and bounded by 2D cells. So essentially this is the criteria we have. Every cell is bounded by number of cells, 2D cells, in the hope that the D will become the continuous dimension in the limit. Because as we know, you have to sorry, I have to close the window. So the way we do it is that we label each cell with a set of integers, let's say D integers. And we assume the existence of shift operator Z alpha such that it takes us from one cell to the neighboring cell. So essentially you will have something like that, or something like that. So the property of the shift operator is very simple. So it acts on the function of these discrete variables, and it shifts along a certain direction alpha, so that it is n beta plus delta alpha b. So this is a shift operator along the alpha direction, where f is a scalar function. So this is the definition of the shift operator. Now, E alpha forms a basis in d-dimensional linear space. And then we introduce, of course, the inverse shift operator, which, just an arrow in the opposite direction. And E alpha inverse FMB is FMB minus delta alpha B. So in other words, E inverse is really 1. So we have to associate actually an order. So suppose that I have more than one shift operator, so that I have E alpha, E beta inverse. So the question, how would this work, is that first you start with the E alpha. So it acts on everything in front. So it acts first also on the this E beta inverse and the F. So you get E beta inverse n plus 1 and the F, and then we act with the trying to remove the no. Ooh. Yeah, okay, very good. So because part of my screen was blocked actually, so I cannot read. So essentially, as you see, this first acts on this, and then you get E beta of n plus 1, and then F of n plus alpha, and then now we act with the E beta inverse, because now this would act on this, so you get F n plus 1 minus 1. And we define the D-tangent operator E alpha, defined by half E alpha of n minus E alpha inverse of n. This actually, in reality, this basis in the limit really becomes the d over dx alpha in the limit. So we are really constructing things in such a way that the continuous limit would become something that we are familiar with. Now, how to proceed actually here? So essentially, the main idea is that from lattice gauge theories, actually, we know how the Dirac operator is constructed there. And from the structure of the Dirac operator, we will try to reconstruct actually, say, the curvature and things like that, because it's known actually that usually if you have spin manifolds and you know the Dirac operator, then you know more everything about the geometry of the space. So this is actually our starting point. And so essentially we take, with a certain cell, then we take a D Euclidean dimensional tangent space. So that's really just a flat space, essentially, with inner product EA, E beta is delta AP. So somehow, it's the idea that in the limit, the tangent space is the same. So we retain the tangent space even for discrete spaces. So essentially, once we say you have a D or 2D cells, so that defines for me a D. And from this D, with every cell, we associate a tangent space, or if Euclidean space, essentially in this case, with our product EAB delta AB. And obviously, this the inner product is invariant under rotation, SOD rotation in this case. It would be just SOD invariance. And in this, actually, EA is a basis in this tangent space. And so we construct EA as a linear combination of the E alpha we defined before. And as we know, the soldering form is the connection between the bases, the discrete base in this case, which is the E alpha, and the Euclidean tangent space. So everything now is really a function of n. It's the only variable we have. And we can invert this relation, of course. We assume that this is invertible. And then we get E alpha n is E alpha A, E alpha of n. So this actually will be like the Vierbein. But now they are really functions of discrete variables. So how to proceed from here? So we looked actually at the construction of the Dirac action in lattice gauge theory. And there actually the action is really written in this language, It is written as psi dagger of n. So we are really assuming that we have a Euclidean space. We are not touching now Lorentzian spaces, just Euclidean spaces. And so Dirac action of psi dagger gamma alpha along the alpha direction, and psi shifted to the right minus psi shifted to the left. This is the definition actually, and as you see, we can write it in our language as E alpha of n psi of n minus E alpha inverse n psi of n. So this is actually the usual lattice gauge theory Dirac action. So the psi actually, as we know, you have d of them. So they are going to transform, say, in the spinor representation of SOD. And obviously, this R of n is the exponential of lambda AB, gamma AB, and gamma AB is the Clifford algebra in this Euclidean space with the SOD local invariance. Well, actually, it will become local in a minute, but for time being, just SOD invariance. And so obviously, we really have to introduce also the analog of the spin connection. So how to do that? Because this is really in flat space. Even in lattice gauge theory, you can think that how can I make this symmetry local, the SOD, how can you make it local? And so you try actually to localize this symmetry. So you introduce a connection. So we introduce a connection, and this connection actually is a combination of, a rotational exponent of an element. So it's an element of the Lie group actually. So it's the exponential. Use the exponential map. These are generators of SOD, and this is the spin connection lives here now. However, we have to associate this also with the shift operator. And the reason, of course, is that here you have this shift actually to the right and to the left. So we have to generalize this to curved, eventually will become curved spaces. And so we introduce this operator R alpha of n is some combination. It's a combination of local rotation and shift operator. And then actually this R alpha of n is required to transform covariantly R, capital R alpha, R inverse n. And then this omega alpha of n actually, which is really the analog of spin connection, doesn't transform in the usual way because it's combination with the shift operator. Now, obviously, then a invariant Dirac action is a combination now of the gamma alpha, but the gamma alpha we have now because the space is the gamma A is Euclidean, and we would like actually to, the R alpha is related to discrete space. We have to connect them with the soldering form, which is E bar A alpha gamma A. And in this case, actually, you obtain the analog of Dirac action in curved spaces, but now the space is discrete, and in the limit it becomes curved. In addition, we inserted density. Actually, this density, one would have thought that this is nothing but determinant E, but it turned out that it is only in the limit it becomes the determinant E. Otherwise, it's not actually. So, having armed ourselves with local form of the rotational operator, now we construct analogy with the Cartan structure equations. We construct what is will become the torsion operator. Actually, here is differential form, which is dE plus omega wedge E, and R, which is d omega plus omega wedge omega. So I would have to, imitate this now. How can I imitate this? Well, we have actually these local operators at our disposal. So we follow now the lead from lattice gauge theories, and we have these operators, which for lattice gauge theories are the same, but there's nothing curved. They have no omega there. So we take these operators exactly the same, but now combined with the rotations. So we have actually the torsion operator now, which we defined as a torsion of discrete space. And then what we do, we sandwich the soldering form, or actually here it is Clifford algebra valued this E beta, when I write E beta, as we said, is this will become E beta A gamma A. So essentially everything is Clifford algebra valued. And remember, actually, the R alpha are proportional to the Lie group generator, so they're exponentials, actually, exponential of the generator, the gamma AB, essentially, in this case, and with the gamma. So you see one gamma is sandwiched between the gamma inverse and with shift operators in between. And then we subtract, because it's like a difference operator, and then we antisymmetrize. Okay? And the R alpha beta is also very similar to what's taken in lattice gauge theory, in which they take R alpha, R beta, R alpha inverse, R beta inverse. Yeah, however, we have a difference is that we do antisymmetrize with respect to alpha and beta. Usually this is not done in lattice gauge theory. There actually, what is done is that they subtract the leading term, which is 1. So they subtract 1, and the second term will be the group generator. But here we actually define the tensor, and to define the tensor, we better do it this way. And then actually, the limit, this has all kind of symmetries that we desire symmetries. So this R alpha beta, actually, we have to divide by the scales. So essentially here we assume for generality that the scales in every direction alpha and beta are different. So we write this, and then we get actually this expression, which is, again, if you are familiar with lattice gauge theory, it's exactly the expression of the Yang-Mills field, except that, with the antisymmetrization. And one can easily show that actually only for 2, 3, and 4, this R alpha beta we constructed would really belong to the Lie algebra in this case. It means the one can cancel and there is no linear term and no higher terms. It's simply proportional to the generator, which allows us to define actually the analog of the Riemann tensor, and then we also can write down what the curvature scalar is. Now, from the hermiticity of the Dirac operator, we can obtain condition on the density, because we have a density here, nu of n, and it turned out actually that this density has to satisfy an identity. And this identity looks, complicated. And, one can check that it is not actually determinant of E, but it will become determinant of E only as a limit. Okay, the above expressions that we wrote, one can easily show that as the scale and alpha go to 0, that what we wrote as the torsion operator becomes the T alpha beta of A, which is the torsion, with respect to the Poincaré group in this case. And R alpha beta AB will become the somehow the Riemann tensor, but with the 2 Lorentz indices, and it can be changed with the soldering form or the Vierbeins into the usual expressions. So essentially, as you see, this is my expression, exponential with all these exponentials. It takes this nice form, and one can easily show that it goes to d alpha omega beta minus d beta omega alpha plus higher orders of L if I make a Taylor expansion in the powers of L. So obviously it does have the proper limit, and here actually these are difference operators for finite L. So here I didn't assume that L goes to 0. I assume that L is small, and I made a Taylor expansion in function of the little L. And here I have L alpha. It means, every direction has its own scale. So I can have more, not exactly the same scale. It could be rectangular. Okay. Then actually as a trial, we did the 2-dimensional example, and we see actually what happens actually. And in this case, we discovered that you really, in the 2-dimensional case, you look at this omega alpha of n, it really becomes a cosine and sine function. So you're really summing infinite series here actually. And this is for finite length. So these are exact expressions. And then for simplicity, just want to see if we can solve these equations, because they're quite complicated, because we will not get differential equations, we are going to get difference equations. And difference equations usually are notoriously difficult to solve. Anyway, so here actually in 2 dimension, we are going to get two connections, omega 1 dot and omega 2 dot as a function of n1 and 2. And then they will have we'll have two equations actually, These are the torsion equations. We are setting the torsion to 0, and it means we have two unknowns, two equations with unknowns, but they're really transcendental equations, you see. They're functions of sine omega and cosine omega. So one has to solve for sine omega and cosine omega. And indeed, actually here, we're able to solve the two-dimensional case. Higher dimensional cases, one can only solve numerically, actually. In dimensions higher than 2, one has to do numerical solutions. But for 2, we really we can solve this equations, and they are in form of arc sine and arc cosine, essentially. E squared, we have only one variable now, which is the E, because the soldering form can be put in function of one variable here, actually. We assumed actually as a special case. So you can get this expression, and the curvature tensor has only one component here, one independent component, and it's a sign of something like that. So you really get nice finite expressions. And this is say Riemann tensor, and this is R, as you see, it's proportional to it apart from the factor E minus 2. So later, actually, I think I have two colleagues here at the American University of Beirut, and they experts in computational physics. So they did the numerics for this example, and so we consider actually what will become in the limit a two-dimensional sphere, and first they mapped how many discrete points you have to take, and and it turned out actually one really can get a nice approximation for a sphere if we take the number of points in each direction. Remember, we have n1 and n2, so it's like 15 square points here. It really becomes it becomes the limit actually. And here actually it tells us how many points you are using in each case. So for 15 points, for example, you are using 1,000 discrete points. So you see things really go to the limit. We measured also the what we call the Euler characteristic, and of course, you really get 2 very quickly. To really get the continuous limit, actually, we start with the line, and then we, what do we do with the line first, actually, and then we try to generalize this. And with the line, usually you take the line, you divide it into n pieces, and then you take this infinitesimal length L over n, and then the coordinate becomes x alpha, epsilon, and alpha. But actually, the x is finite, actually. If you take a point in the line, it's finite, and therefore x is finite, but the n goes to infinity. So you have to make the little n also goes to infinity in the limit. So it's very delicate. And so that actually we take n over n, capital N is x0 over L. And as a test, actually, on the E alpha we took before, you notice that E alpha becomes d over dx alpha. So it's really, it's the right limit. And similarly, we can show that this v of n I took really becomes, it really becomes determinant to alpha. You get an identity, you do a Taylor expansion, and then you get that v of n is determinant to alpha. So of course, the next stage now we will consider higher dimensional spaces and all kinds of discrete spaces. However, so let me summarize actually my talk, since my time actually I have only a couple of minutes left. So we have achieved a formulation of discrete gravity based on the idea that the rotational invariance in tangent space is the same. That it's because the tangent space is Euclidean, we did not discretize the tangent space, we kept it continuous, and we assume that it is the same in the discrete case and the continuous case. And this, for example, if you put a spinner in this space, the number of components would determine the kind of symmetry you have. Now, we avoided actually the biggest difficulty actually in defining curvatures. If you look in the literature, and I did make a huge search to find actually what kind of definitions of curvatures and things like that they construct, and mostly, it's like attempts by Reggie and others in which it's related to the angles of the tetrahedrons and things like that in 4 dimensions. And once you follow that route, it's very difficult to obtain a connection with a continuous limit because you're taking tetrahedrons and angles and things like that. So it's not the same way. So failure of Leibniz rules for difference equation is avoided. Actually, this is the biggest hurdle because usually what you want to do, suppose that I would like to follow the simplest approach. I take my shift operators and I construct the Christopher connection, the analog of the Christopher connection, which we can do. But then actually the next step in which you have to take another derivative, then things would really go bad and you'll not be able to do the simple analogs actually in that case. So here, with the Cartan equation that everything is like first order, you avoid that difficulty. So the advantage of our construction, the definition of curvature gives manifest continuous limit to those of differential geometry. In future, actually, the aim is to apply this formulation to something that we did earlier with Arancon on the quanta of geometry, where we showed actually that that the spheres can act as quanta of geometry in the commutative geometry, and again, actually, also to see actually if we really can apply it to cosmology of expanding universe, where you really have a unit and in which the volume of the space will become some quantized multiple of this unit. So, that's all, and, thank you. I can't see now. Okay, here.
Let's see if there are any questions. Olaf.
Clear that this discrete gravity has a version.
Can you repeat?
Is it clear that this version of discrete gravity has a discrete version of the morphism and the rest?
Did you hear that, Ali?
No, I didn't hear anything, no.
So is it clear that there is a discrete version of diffeomorphism and Lorentz invariance?
Right. So actually, I think the hope, see here, of course, we don't have diffeomorphism, but we try actually to understand, up to now unsuccessfully, is that the idea, because this space is constructed out of cells, and the question is that you have some arbitrariness in the configuration of cells or going from one cell to another. So this idea eventually will become diffeomorphism invariance, but the idea, the link between this arbitrariness in the choice of cells and diffeomorphism invariance, there's a real link, but we still were not able to formulate it yet. And local Lorentz invariance, of course, is there by assumption. It is already there. We assumed it there.
There is also a question from Hermann.
Actually, I have 2 questions. One is, can you generalize this to Lorentzian signature? And the second question is, with the fermions on the lattice, one usually has the doubling problem. Is this avoided or is it irrelevant?
Shall I repeat the question, Ali?
Yeah, please. Yeah, I cannot hear you.
So can you generalize this to Lorentzian signature was the first question, and the second question is, can you avoid fermion doubling?
Right. For the first question, Lorentzian, as you see, for Lorentzian signature, the main hurdle, if you don't want to do numerics, is the non-compact nature. And because now you see we have this exponential of the Lorentz group, so once you have this in the exponential, then you are going to get non-compact expressions. So this I don't know how to do actually, because and for the other question related to doubling of fermions in Euclidean spaces, again, it is the issue that I don't think we will be able to do better than what the lattice gauge theories did, in which they have, I don't know, the Ginsburg-Wilson trick in going to one dimension higher or something like that. But we have not really, you know, we are not sophisticated enough because we're still trying to understand how to make this approach more mathematically consistent. You know, we are still lacking definitions and things like that. And you know, I tried to convince Alan to get interested, but he's not. You know, he's working on his different problems now. So we need more mathematical, you know, uh, mathematical foundation. Yeah.
I also have a maybe related question. It seems by keeping the tangent space continuous, it seems that you sort of build in a certain dimensionality of the continuous limit. If you go further, do you think so? I mean, this probably prevents this kind of gravity from spontaneously appearing as 4-dimensional or 3-dimensional or whatever. But do you think it's general enough to allow for things like topology change?
Yeah, I don't know actually whether it would allow topology change. I think, you know, to us is, you know, I see your point actually, that why should I make the tangent space continuous and keeping the other discrete? But, you know, actually the idea that if you think about it actually, you know, with all, especially from particle physics, the tangent group plays it is somehow built in, you know, so essentially why SU3 is a symmetry, simply you have 3 colors. So essentially here the idea that, the same idea that you really have, say, D component of the spinors. It's simply a number, right? And then we said that why actually this number doesn't really become the basic symmetry, because even let's gauge theory actually, the SU3 symmetry is taken to be a symmetry, right? So here is the basic idea, but should one go further and assume even that the symmetry will become, you know, some kind of discrete symmetry? Possible, but I think here as a first step, it's safer to go through this approach. And as I said, we are really completely driven with analogy with lattice gauge theory, where actually the SU3 symmetry, the SU2 symmetry, and so on are kept intact. Also, the space is discrete. So this is the analogy actually. And we know Lorentz symmetry is like an internal symmetry for gravity. So.
Okay. Let us thank Ali again.
Thank you very much.